Alright, so now that you guys are pros at drawing Lewis dot diagrams and determining VSEPR shapes, we can talk about molecular polarity and intermolecular forces, because they build upon both of those lessons. So, our first example, determine the polarity of CH3F and state the intermolecular forces present in the molecule. So the first thing we need to do is we need to draw the Lewis dot diagram and figure out the VSEPR shape. So when we draw this, we get C in the middle, 3 H's, and an F around it. So on carbon, we have AX4 because there are no lone pairs on the carbon. This means it's tetrahedral. Remember, tetrahedrals exist in 3D, so we would draw this in 3D with 2 H's in the plane of the page, or an F, doesn't really matter. Something out of the page and something in the page where the bond angles are all 109.5. So, oops, I forgot that one of these needs to be an F. Alright, so when we draw these, we see that not everything cancels out. So the electronegativity difference between carbon and hydrogen would be 0.4. And there would be just a little bit of an arrow pushing in because carbon is actually a little bit more electronegative than our hydrogens. However, fluorine is extremely electronegative in comparison with carbon, which is like 2.6, I think. So this one is pulling out towards fluorine a lot more. Now all of these arrows with the hydrogens make a bit of a tripod that are pointing towards the fluorine, and then this arrow for the fluorine is pointing again away from the carbon. So in general the polarity is pulling towards fluorine, and this would be a polar molecule. Another way to tell, and the easiest way to tell, is those two rules I gave. If everything around the molecule is the same and there are no lone pairs, then this would be nonpolar. However, if there are different entities around the central atom and or there are lone pairs on the central atom, it is most likely polar. So, because not everything around around the central atom is the same, this will be a polar molecule. Alright, now, what intermolecular forces are present? Well, we always have London dispersion forces, regardless of what this molecule is. We also, in this case, have dipole-dipole because there is a polarity in the molecule. However, we do not have hydrogen bonding because there is no hydrogen directly connected to an oxygen, fluorine, or a nitrogen. Although there are hydrogen and fluorine atoms in this molecule, because they are not directly connected, this cannot count for hydrogen bonding. My second example asks us to list the following compounds in order of decreasing melting point from high to low. So for this, we need to determine if the molecule is polar or not to determine its intermolecular forces. In doing so, we also need the VSEPR shape, and then because of that, we would also need Lewis dot diagrams to get started. And so what we're going to do is we're going to go through and we are going to do our best to assign their forces without drawing them. If you need to draw them, go ahead and discover their polarity to see where we're at with them. Iodine. Two iodines connected to one another would have an electronegativity difference of 0, giving us no polarity, and this will just have London dispersion forces. Now I've listed graphite here. So graphite we know is a network solid. So it doesn't have intermolecular forces, which are interactions between two molecules. It in fact has intramolecular forces of covalent bonding, which makes it extremely strong because of the way the carbons are arranged. CCl4 is a tetrahedral, carbons in the middle, with 4 chlorines around it. Because everything's the same and there's no lone pairs around that, this is going to be nonpolar again, and we're going to have London dispersion forces. CH3OH. With this, we have a carbon with 3 hydrogens around it, and then one OH connected. So because there's an OH directly connected together, we know that this must have hydrogen bonding. This is also a polar molecule. Copper as a solid is a metal. And because there's nothing else with it, it's not ionic, it's not molecular, it can't be. So this is a metallic bond. Remember, we put these on the same kind of playing field as an ionic bond when we're listing melting or boiling points. Lastly, this is acetone. Acetone, when we draw it out, I'm just going to quickly draw it here. We get carbon in the middle and oxygen and hydrogens. Because the oxygen is not directly connected to the hydrogens, we don't have hydrogen bonding. However, because there's one thing different around the carbon, not everything's the same, this is a polar molecule and we have dipole-dipole forces. Now, highest boiling point will be our network solid. So we'll have C graphite. Then next will be something that's metallic or ionic, so our copper solid. Next will be our hydrogen bonding, so this is methanol. Next is dipole-dipole. This is our acetone. And next we're coming to our London dispersion forces. Now remember, London dispersion forces are affected by molar mass. Iodine has a massive molar mass in comparison to carbon tetrachloride. So iodine will have stronger London dispersion forces than carbon tetrachloride will. So this is our order from the highest to the lowest melting point, determined by intermolecular forces.